Energy is defined as the ability to do work. This is the one of those sentences that physicists always use to explain what energy is, but it assumes that the reader knows what work is. So, in the first lesson about this chapter, about work and motion, we are focusing on what work is and on the most important equation that you'll use in this chapter. If you push a chair along a floor, or for the sake of this demonstration, if I push this pen on top of the mechanics book, what am I doing? I am using the energy from my body to make the marker, the pen, move, right? So there is energy that is being transferred to the marker, and the marker is going to feel this energy as work. And what is the means by one is passed on to the other? Is through a force that I'm applying here with my finger. Okay, so there is a force applied to the marker. As a consequence, the marker is going to move a certain distance on top of this book. I'm sorry. And the product of these two is going to be the work that the marker is going to have. Okay, where did the work come from? It went through the energy that my body, through my finger, applied to it. Okay, so the energy in my body was able to produce work on the marker in this case. So work is the ability to transfer energy via an external force, my finger, acting on the pen. Work can be positive if it contributes to motion, like the example I just gave. Can be negative if it counters the motion. For example, a friction is always going to be a negative work because friction always, by definition, opposes motion. Or null if it has no effect in motion. Let's see first mathematically how to represent work. Work is represented by a capital W. Again, that's the reason why I don't use W as the letter for weight, because it's already taken for work. Okay, so as you already know, I use FG for weight. So it's going to be equal to the force, whatever force we're talking about, times the displacement the object has, times the cosine of the angle between the force and the displacement. Okay, because this notation means the angle between F and D. In any object that is moving, if you have a multitude of forces, you can study the work that each one is going to have in relation to that object. And by using this formula, you can analyze if the work is contributing to the motion, or if it is countering the motion, or if it is having no effect whatsoever in the motion. Okay? If F and D have the same direction, then this angle is going to be 0, right? Force direction angle is 0 means that the cosine of 0 is 1, so the work is going to be positive. Positive work means that the force corresponding to that work is going to contribute to the motion. If the force and the displacement make a 180-degree angle, that is, if you have a force in that direction, or better yet, if you have a force in this direction, but the object is going that way, so the angle is 180 degrees, cosine of 180, as you know, is -1. So that means that you have a negative work. What does this mean? Means that the force is taking energy out of the object, right? Is resisting motion. On the other hand, if the force and the displacement are perpendicular, let's say that the object is going that way, but the force is like this, making a 90-degree angle. This means that the cosine of 90 is 0, as you know, and you'll have no work. It means that this force is not contributing at all, is not contributing or retrieving or taking energy out of the system. You have no work. Let's see an example. A box moving along horizontal surface. You have a force that way, you have the friction this way, you have the weight. The object moves indeed from here to here, so this is the displacement. The work done by force F is positive because the force and the displacement, they have the same direction. Angle is 0, means that you have positive work. F is contributing to the motion, as you can see, right? The friction has the opposite effect. You have the displacement that way, the friction is this way, so you have a 180-degree angle, means that the friction is having a negative impact on the motion of the object, so to speak, okay? You have negative work, means that the friction is taking energy out of the system, the box system. The weight points down, okay? The displacement is to the right, so this angle is a 90-degree angle. The weight has no contribution at all to the motion of the object, so it have no work. Doesn't matter if this is light or heavy. In this particular representation and simplification of the situation, the weight is not going to either take energy or take out energy of the system. Okay? Work is measured in the same unit as energy, which is the joule. All right? If everything that you are using in this formula uses the international system, namely, if this is in newtons, this is in meters, then the work is in joules. A very important word on wording. Sometimes you will read things like the work done against a force, against friction, against weight, or against gravity, etc. What does this mean? This is the work done by another force that is just enough to overcome it. Okay, we are going to see later on in the next lesson, in example 4, situations in which you have this wording, and back then I'm going to explain again what it means. Let's now talk a little bit about kinetic energy. I bet that you already know this. Kinetic energy of an object is the energy that object has due to its motion. It needs to be moving in order to have kinetic energy. It needs to have a certain speed, and the object, being an object, needs to have a certain mass. And the value of the kinetic energy is given by this very famous equation, 1/2 of mv squared, okay, in which m is the mass of the object, v is the speed of the object, it is squared, okay? So doesn't actually matter if this is positive or negative. I didn't pay attention to the fact that I didn't say velocity, it's speed, right? Even if this was a negative value, if it was velocity, by the fact that it is squared, it will pass to a positive value. And by looking at this, you will see that the impact of the speed is much greater than the impact of the mass. If you have a truck or a car moving at in a road with a certain speed, obviously the kinetic energy of the truck will be bigger because the mass would be bigger, right? But now let's take the car. Let me rephrase what I just said. Let's say that you have a truck and a heavy car, but the truck is twice the mass of the car, so and moving at the same speed. The kinetic energy of the truck would be twice as big as the kinetic energy of the car. But if you have the car or two cars with the same mass, and one of them is traveling at twice the speed of the other, then the kinetic energy would be 4 times as big, right? That's the reason why it is so important for people to take care when they are driving a car, because doubling the speed means that the energy associated with the car and everything in it is 4 times as big, okay? If an object changes its speed from u to v, then the change in the kinetic energy given by delta CAIE, delta is the Greek letter that is usually representing a change of something, in this case change of kinetic energy, is given by the final kinetic energy minus the initial kinetic energy, which is basically 1/2 of v squared. For final we use v, minus 1/2 of u squared. U is a symbol that we use for the initial velocity. We can factorize initial speed, sorry. We can factorize 1/2 of m, the mass doesn't change. So the change in kinetic energy is just going to be equal to 1/2 of m v squared minus u squared. If the object speeds up, then v is bigger than u, and you have a positive change in kinetic energy. If the object slows down, the v is smaller than u, so this is going to be negative. You have a negative kinetic energy. If you have a constant speed, then v equals u, and you'll have no change in kinetic energy. Okay? This is, I think, trivial. Now, let's go to the most important equation regarding this chapter. The total work applied to a system, the total work done by all forces applied to an object or a mass body, is equal to the change in kinetic energy of that body. Think of this for a bit, because if you think of this for a bit, I think that it will make sense in your head. Imagine whatever object, and you have a multitude of forces applied to it in different directions, okay? Doesn't matter how many. If you would be able to calculate the contribution in terms of work of each individual force by using that formula that we learned before, and if you would add them together, what would be the outcome in the perspective of the force? It would be a change in its speed in a certain direction, right? Actually, here the direction doesn't matter, but it will definitely have a change in speed, assuming that all these works do not add up to zero. Okay? So there will be a change in the kinetic energy of the object. This happens all the time. So again, the total work done by all the forces acting on a body is equal to the change in kinetic energy of that body. Mathematically speaking, the work done by the resultant force equals a change in kinetic energy. And you are going to use this equation a lot. What is going to be different from question to question is this part over here. The number of forces applied to the object, the calculation of the contribution of each individual work, but then that part is always going to be the same. Let's start with simple examples. In this case, you only have a single force, this F, applied to this object, and as a consequence, it moves in that direction and it has this displacement. So let's apply the formula. The work done by the resultant force equals a change in kinetic energy. How many forces you have? One. So the resultant force is just this force. So you basically just have the work done by force F equals a change in kinetic energy, which is the final kinetic energy minus initial kinetic energy. What is the work done by the force? Is the force times the displacement times the cosine of the angle between them, which is 0. So it is just equal to this, which we already know it's 1/2 of m v squared minus u squared. So if imagine that the question was asking for you to calculate the intensity of the driving force, knowing the two speeds and the mass of the object, we could just by doing this. Okay. No, actually, it's not a driving force. This is just a product of the force and the distance. So in this case, the work would be just calculated by knowing these values over here: the mass, the final velocity, the final speed, and the initial speed. Let's say now that we have two forces. Besides the force F, you also have a friction that way, opposite, obviously. Then the equation is still the same. The work done by the resultant force equals the change in kinetic energy. What are the two forces that you have now? The force F and the friction Fr. So you have the work done by force F and you have the work done by friction. So you add them together, which equals again the change in the kinetic energy. Now let's look at each one individually. I already talked about this. Nothing changed in relation to force F, so that's just F d cosine of 0. But in relation to friction, you have the value of the friction, the intensity of it, the displacement, and the cosine of the angle between these two. Displacement is that way, friction is this way. You have cosine of 180, which is -1. So this is just going to be F minus This is going to be a negative value, right? So it's going to be minus friction FRD, which means that we can factorize the D, and we will just have FD minus FR times D equals 1/2 of mv squared minus u squared. Okay, so again, this part over here is 1, this part over here is minus 1, and this is just the outcome of factorizing the displacement. One very important thing, I'm following a mathematical procedure, but chances are that soon enough you are going to analyze the circumstances and see for yourself what is going to be the cosine of the angle. Either it's going to be 1 or minus 1, or in some situations 0, and you are going to put the corresponding sign yourself. You are just going to look at the circumstances and see if the force is contributing to the motion in a certain displacement, in which case you put the value of the work as positive, or if the force is trying to take energy from the system, in which case you are going to put the minus. That's what I do myself, but I'm just focusing on using the cosine for you to see that there is a mathematical reason for you to choose between a plus or a minus. Again, the shortcut is if the force is contributing to the motion in a certain direction, then it's a plus, it's a positive work. If the force is trying to take energy from that specific motion, then the work is going to be negative. So you put a minus.